Sorry. Okay, I'll do it again. So our next speaker is Bruno Kamdem, and is at NYU Tandon.
Yes, it's an incredible honor to be here. Yeah, okay, yeah. That's good. So, yeah. So it's an incredible honor to be here to present this paper, which is a joint work. I first met Peter some 4 or 5 years ago, thanks to Professor Jeman, who's here, to whom I'm equally very grateful. And Peter, I knew as a very intellectual giant in the finance community, but yet very personable. And we met again in Boston, and later he invited me to give a talk at Kamdem, which I did. And after that, he invited me to teach an ESG class, an ESG finance class, sustainable investment, which I did. So we always gonna miss him, and we are gonna try to emulate his legacy in our daily life. So this work actually has three components. The first component is a resource allocation part. It is a joint work with Mustafa Pemi at Towson University. So in the first component, we use optimal control theory to derive an optimal extraction rate as a function of the initial oil price when the emission rate is less than the threshold set by the government, or as being the optimal taxation rate when the emission rate is greater than the threshold set by the government. So the second part of the work has to do with risk management. Here, we have 2 subcomponents. The first subcomponent has to do with where we derive a carbon auction derivative and present that carbon auction as a put or a call option on carbon permit. And the execution of that call option actually is contingent on whether the emission level of the company is less than the initial threshold set by the government entity. So I present both work at the seminar at NYU FRE, Financial Engineering, and both work are on YouTube. If you can just go and Google my name, Bruno Kamdem, and NYU, you'll find the 2 presentations on YouTube. So subsequently to my last presentation, which was in December, Peter suggests that we should look at the emission rate instead of the emission level and integrate the emission rate into the carbon permit. And that's what he said. And he recommended that we should integrate that extraction rate to make it a 2-factor model, right? And following his recommendation, we went along with my co-author, we worked very hard, and we came up with a workable closed form solution of this new carbon model. So next we're gonna talk first about the carbon tax in our introduction very quickly, versus the carbon permit, and look at all the climate policy surrounding it. And we talk about the carbon emission rate as possible proxy for the interest rate. And then look at the option pricing model that we derive, and look at how we explain how we came up with the derivation. And finally, we're gonna conclude as some sort of term structure of the emission rate to tame or control climate change. So since climate change is a pressing existential threat, government in the world, around the world, are going to need a mosaic of integrated energy solutions supported by policy package aimed at substantially reducing carbon emission from the industrial sector, right? Because most of it come from the industrial sector. And talking of ESG, here we're really focusing on the E pillar, which is the environment. So the question is really, how can government successfully reduce CO2 emission? Because CO2 is the major component or major current contributor to climate change. You know, CO2 is released whenever fossil are burned. So to achieve this goal, there are two main climate policy. The first one is the carbon tax, and the second one is the permit market, the carbon market. We have in Europe the ETS, which is the European trading system, and we know that last year China came up with their own carbon market, and we have an existing one here in America, mostly in the West Coast, in California. I think I heard this week that Virginia is considering joining the carbon market out in California. So here we talk about talking about our carbon market. We come up with the notion of auction, and one of the reasons why economists and investors are attracted to auction is that the auction really gives the commodity market the option to self-determine the right resource to achieve emission reduction while still making money. So in this section, in this particular part of the paper, we track the carbon emission rate using a mean reverting process. And this approach is not new, actually. It is similar to what is done with the interest rate. The interest rate is usually regulated by the Federal Reserve and affect the capital market, the retail market, and sometimes they use, as we know, recently the chair and the president met to see how they can control inflation by just putting some kind of threshold or pushing the interest rate. So that's how we're going to be looking at this carbon emission rate. And our work and technique in this section follow the likes of Hu and White, Hu-White, which derived the paper, the two-factor model, Hu-White, which derived a two-factor interest rate model using the Vasicek model and the extended CRIR, which is the Cox, Ingersoll, and Ross model. So here is our carbon model, right? In the two-factor model here, what's happening is on the one hand, we have a carbon option permit, which is our main factor, and this carbon option permit is random and follow a geometric Bruno motion. And the second factor here is the emission rate, and we let the emission rate be part of the drift of the carbon permit, in the sense that the emission rate contributed to the carbon permit, and the emission rate here is a mean reverting process. So in this model, mu is the drift of the carbon permit, and lambda is the coefficient that measure how much the emission rate contribute to the drift of the carbon permit process. And sigma 1 here is the volatility of the carbon permit, and M here is the mean of the mean reverting process, and B represent the mean coefficient, meaning it measures how much the emission rate revolve around the mean. And sigma 2 is the volatility of the emission rate. So evidently, Z1, the carbon permit process and the emission rate are correlated through the winner processes, and the correlation coefficient is rho. So here, this is how we go about deriving our model. We first get UT, which is the emission rate, and we use UT can be gotten very simply using technique of partial differential equation. To get ZT, we apply Atto lemma by letting YT be ln of ZT plus delta UT, where we define delta to be lambda over B. And then we use Ito isometry, which is very, very important in the derivation of this carbon call option. And we talk about that a little bit later. And then we make some equivalence of variance. W3 is actually a combination of W1 and W2. And we define the probability distribution function and the probability density function, finally get our carbon call option. And we have not derived the carbon put option as of this presentation. We have an upcoming presentation where we're going to be in Bloomberg, possibly in the next 2 or 3 weeks, where we're going to be talking about our put option, both in about 5 minutes. It can be a lightning talk. So here, how do we use the Ito isometry? So because this function here is elementary and bounded, we can find its variance using Ito isometry. For reference, you can look at this book, Bernd-Oxendorf, Stochastic Differential Equation, an introduction with application. So this is a very important theorem that thankfully helps us to find the solution to this two-factor carbon model in a closed form. Now, here, so we have a call option, which is a function of the initial time S, the maturity time T, the initial carbon permit Z, and the initial emission rate, which is U, and K is defined as you see there. K is a function of the initial time, the maturity time, and the initial carbon rate, as you see. What you see there, lambda over B, is just delta, we just spoke about earlier. So it's quite a bit of manipulation here. We look at the variance sigma 3, much manipulation that we do, and then come up with this closed form formula, which is a little bit, we can make an analogy, we can establish an analogy between this closed form formula and the traditional stellar Black-Scholes formula. We see that in a couple of minutes. So next, so we graph, right? This is a continuous time model, but discrete time model. But to graph it in our code, we have to discretize this part of our results. It's sigma 3 because it's actually a pretty complicated, complex formula. So here we minimize lambda. Remember that lambda is the coefficient that measure, right? It's a coefficient that measure how much the mean reverting or the emission rate affect the carbon permit. So here lambda is a little small. And we see a little jump at the beginning, and then it goes down, and then the Carr option goes down. But what happened when lambda is here. Lambda is 4%, right? What happened if we push lambda, for instance, to 10%? You see what happened. So here, in the second case scenario, here 10% of the mean reversion affect the drift of the carbon permit. So the carbon call option drop from 17 to 14 and then jump. So we have to, and something to understand here is that this carbon option is exercised by the polluter, right, as such as a penalty, because the government set the threshold or the rate. Here we can talk about the emission rate. If the polluter pollute more than the emission rate, or if the emission rate of the polluter is more than the emission rate set by the government, then they have to buy the allowance in the carbon. They have to exercise this carbon option. Now, what happens when the lambda is equal to 0? When lambda is equal to 0, we see here some sort of standard Black-Scholes model, right? So when lambda is equal to 0, our model become similar to the Black-Scholes model. So what have we done here? We successfully solved the dynamic of the carbon auction trading system. And here we derive the call option and the carbon put option in closed form. We provide the complete formula of the carbon put option later. And this carbon option permit starts as a geometric Bruno motion, and it's driven by a mean reverting rate. And the carbon call here, call option here, as we said earlier, is quite similar to the classical Black-Scholes model, but it is not the Black-Scholes model because the drift is not linear. In our case, the drift is exponential. As t goes to infinity, what we have is the carbon model, although may act as a Black-Scholes, but it is not Black-Scholes. And when t is very, very, very large, the mean reverting contribution still kind of stay. Okay, so the next thing we want to talk about is the term structure of carbon emission rate. Something to think about is to think of decreasing emission rate as some sort of decarbonization rate, right? Achieving decarbonization involves pricing carbon through regulation, right? As we decrease emission, we decarbonize. So the trajectory needed to meet the Paris Agreement goal of reducing CO2 by the Earth atmosphere temperature by 1.5 degrees and avoid catastrophic climate change require a very proper calibration of the decarbonization rate, or in our case of the carbon emission rate. So a good decarbonization rate is required to achieve the Kyoto Protocol, or to have global emission by 2030 and to reach the net zero by mid-century. So, and then we can talk about the implication for the commodity market, right? We can talk about the implication of the commodity market, like structuring carbon emission rate to tame the extracting and the drilling activity of a commodity company like oil company or this other company that really heavily contributed to carbon emission in the atmosphere. And we can also think about the implication for regenerative agriculture, something I just recently came aware of by attending a conference. Right? We can structure the carbon emission rate stimulate carbon sequestration. It's something now called carbon sequestration, where company or people are capturing and storing atmospheric carbon dioxide in order to contribute or mitigate emission into the atmosphere. So these are some of the implications of our work, and I think we pretty much done now, and we plan on just completing the writing and having that for publication after our lightning talk at Bloomberg. So finally, I just want to again say something to Peter Carr, who really helped me in my life, along with Professor German, who was here. He was a stellar intellectual and a rare humanist. Very rare can we see a great intellectual, but still as human, and even as human and humanist as Peter Carr. Like Bruno said the other day, Bruno Dupierre, he said the other day at the funeral that in France, there's a saying, people die twice, and the first time, the physical death, and then the second time when people forget about them. And I think, I'm confident, I'm sure that Peter Carr will never die for the second time. And that's what I put this French here, il ne mourra jamais pour la deuxième fois. So we always gonna forget, we're always gonna remember him and live to fulfill his legacy. Thank you.
Thank you. No, I'm not so familiar with the topic, but I was thinking when you were speaking about decarbonization and trying to build in the decarbonization in the model, did you or somebody else think about to do this with a stochastic benchmark? Let's say the temperature average over a year or so, and depending on how actually the temperature evolve determines the amount of carbon emissions given for the next year, to have basically a kind of feedback effect of decarbonization.
Yeah, so we haven't considered this problem in terms of temperature. We only consider this problem in terms of emission rate, right, and carbon permit. So we really limited into to the carbon market, the auction. We haven't looked at the temperature side of it. I think the better models are there to look into that can successfully or very rigorously look into the temperature part of the problem. Nonetheless, our emission rate is stochastic. It's a mean reverting process. It's a random and process, evidently, and our carbon permit is also a born in motion.
Yeah, I have a question about the plots you showed of the option prices. The option price was going down and then increase again in maturity. Is there some intuition behind this?
Yeah, the intuition. Okay, so in that case, the contribution of lambda measure the contribution of the emission rate to the drift of the carbon permit. So I would say that the intuition behind it probably will be when it comes to commodity price. You see, when the commodity price goes up, emission rate evidently going to go up, like the oil price. Price goes up, the emission rate probably going to go up, and you can also think of it as terms of demand. When demand for oil goes up, like extraction activity goes up. So I will define the intuition that way.
Thank you, Bruno. That's very interesting. I haven't seen any application like that, applied to this particular market. And I think it's great that you're cutting a path here. But I do have some questions about the feedback mechanism. let's say that, you know, as we have these permits and people use them, and this happens in a global way, that we'd like to think that it's going to cut emissions, but in fact, what happens is the price of the commodity can also react by increasing, right? And we're ultimately relying on the consumers, not the producers, to cut their demand in order to get the desired effect of these regulations. I'm wondering what your thoughts are, and maybe whether it's in the context of this model or outside this model, about the feedbacks with respect to price, you know, the demand and the supply side, because also as the permits become expensive, regulators go under more pressure to release more, you know, and I'm just concerned about, you know, these the application of these models in general, and maybe I thought you might have some ideas on those two things.
Yeah, that's a good question, David. So if you look at the emission rates, here we're looking at the polluter. So the company that pollute, that go above the emission rate set, you know, we assume that set by the government, let's say maybe in the European Union, they exercise this corruption, right? So the motivation would be to think of this company as exercising this corruption as a way to maybe make more money, right, by trading permits, than making more money than by extracting and polluting the atmosphere. So, and I think that's what's happening in China. They, with the carbon market in China, they want to incentivize company to think about cutting the emission rate or cutting the CO2 emission and make more money by trading carbon permits, right? So what we're offering is, instead of looking at the emission level, as Professor Carr suggests, let's look at the extraction rate and define some sort of term structure of emission rate, right? Extraction rate, emission rate, because that's mostly drilling company, and see how we can adjust, government can adjust the emission rate to control the emission or even the permit, make sure that maybe this company will make more money by trading the carbon permit instead of drilling and destroying the atmosphere. So I would say I will look at it that way, that they can just, because everything really is making more profit. Company want to maximize profit. So why don't we get a profit by trading carbon than destroying the atmosphere? Yes.
We get impatient. Yeah. Thank you, Bruno, for this talk, which was quite interesting. Just to, I have been working on the problem of climate change and temperature and renewable electricity for a while. And I have a grant from the US Department of Energy on the topic. To come back to the first point, which was made on temperature, it is quite interesting. However, we would need to define what would be the temperature that would guide the process, carbon price or whatever. Is it the temperature in the US, or is it the increase of temperature in some places in Africa where it may become too warm? So that's one of the challenges. And to come back to David's comments, if you look at the US at the present time, we have a Democrat president, and still we have drivers who are very angry at the price of gasoline. So it is not clear that consumers are going to behave better anytime soon. This in the middle of many, many other considerations. Thank you.
Thank you, Mr. Chairman. Thank you.